this lesson, we work through a problem which involves an application of Newton's second law as well as Newton's third law. It involves a system of a few blocks that accelerate together. Here is the question. So we have 3 blocks making up a system. The masses of the blocks are 1 kilogram, 2 kilograms, and 3 kilograms, and they are on a horizontal surface that has no friction. And there's a force of 42 newtons that pulls the system to the right. And we are asked to find the acceleration of the system, the tension in the rope, and the force which the 1 kilogram block exerts on the 2 kilogram block. In order to understand the situation, there are 2 important concepts we need to deal with first. Firstly, tension in a rope or a string. The tension exerted by one end of a rope is always equal in magnitude to the tension exerted by the other, and the tension acts towards the center of the rope. So in this situation, we can see that there's a rope joining the 1 kilogram and the 3 kilogram bodies. There's tension in this rope. This tension pulls the 1 kilogram body to the right and the 3 kilogram body to the left, because tension in a rope always acts towards the center of that rope. And the tension on the 1 kilogram body is just as strong as the tension on the 3 kilogram body. We call the tension on the 1 kilogram body T1 kilogram and the tension on the 3 kilogram body T3 kilograms. So T1 kilogram equals T3 kilograms because of this fact that the tension exerted by one end is equal in magnitude to the tension exerted by the other end of the rope. The next important principle that we're going to apply in answering this question is Newton's third law. This states that if object A exerts a force on object B, then object B simultaneously, that means at the same instant, exerts an equal but opposite force back on object A. We call the force which A exerts on B, F on B by A. We call the force B exerts on A, F on A by B. So in this situation, the 1 kilogram and 2 kilogram objects are exerting forces on one another of a Newton 3 kind. So the 1 kilogram object exerts a force on the 2 kilogram object, which we call F on 2 by 1, and the 2 kilogram object exerts an equal but opposite force back on the 1 kilogram object. Now in a free body diagram, we always draw the forces acting on the object, not by the object. So when we draw the 2 kilogram object's free body diagram, we draw the force which it receives from the 1 kilogram. And when we draw the 1 kilogram object's free body diagram, we draw the force which it receives, which is acted on it by the 2 kilogram. Here we have a free body diagram for each of the 3 blocks. Let's start by looking at the 2 kilogram block. In all cases, we have vertically weight of the block acting downward and the normal force exerted by the surface acting vertically upward, because this is a horizontal surface. Notice that the free body diagrams are not drawn to scale. Free body diagrams don't have to be drawn to scale. So for example, actually the 1 kilogram's weight, which is 9,8 newtons, should be shorter than the vector for the 2 kilograms weight, which should be 2 times 9,8 newtons. And that should be shorter than the 3 kilograms weight. And the same with the normal forces. So vertically it's very easy to draw these free body diagrams. But let's focus on the horizontal forces, and let's start with the 2 kilogram. As the whole system is pulled to the right, the 1 kilogram block pushes the 2 kilogram block to the right. And we call the force that the 2 kilogram block experiences because of this F on 2 kilogram by 1 kilogram. So notice we don't draw that force on the 1 kilogram's diagram, but on the 2 kilograms diagram, because we only ever draw the forces acting on a body in a free body diagram. So there's only one horizontal force acting on the 2 kilogram block. That force is part of a Newton 3 pair, meaning that the 2 kilogram block also pushes back on the 1 kilogram block just as strong. So if we go to the 1 kilogram block now, we see that there's an equal and opposite force to that which we've just looked at. That's not the only horizontal force that the 1 kilogram block experiences. It is also pulled to the right by the rope, T 1 kilogram. Now, because tension always acts towards the center of the rope, this tension also acts on the 3 kilogram block, but in the opposite direction. So horizontally, there are two forces acting on the 3 kilogram block, the 42 Newton force, which is the applied force applied to the whole system to the right, and then the tension in the string pulling the 3 kilogram block backwards. So now we're ready to start answering these questions. Firstly, what is the acceleration of the system? This is Newton's second law equation rearranged to make acceleration the subject. We know the mass of the system. It's the sum of each of the block's masses. 1 plus 2 plus 3, 6 kilograms. But what about the net force acting on the system? How do we find that? Here are our free body diagrams again. Let's choose one direction to be positive. Let's choose right to be positive because the system is moving to the right. So notice how all the vectors to the right are colored in red and all the vectors acting to the left in blue. We add all the forces acting to the right and then we subtract from that the forces acting to the left. So let's list them. To the right we have the tension force acting on the 1 kilogram body and the force which the 1 kilogram acts on the 2 kilogram and the 42 newtons. We subtract the forces acting to the left, which are the tension acting on the 3 kilogram body and the force which the 2 kilogram body exerts on the 1 kilogram body. Now remember that the tension in a rope acts towards the center of the rope and is equal in magnitude in each of those two directions. And so the tension acting on the 1 kilogram body is equal and opposite to the tension acting on the 3 kilogram body. And so those two can cancel one another out in this equation. And that simplifies our equation like this. Then remember too that according to Newton's third law, when object A exerts a force on object B, then object B simultaneously exerts an equal but opposite force back on A. So here we have a Newton 3 pair of forces exerted on the 1 kilogram and on the 2 kilogram, equal in magnitude but opposite in direction to one another. And so their effects also cancel out since they are equal and opposite, simplifying our equation even further and telling us that the net force acting on the system is 42 newtons to the right. We can now substitute this into our equation and solve for A, 7 meters per second squared to the right. Notice that the direction of the acceleration is the same as the direction of the net force, which was to the right. Now we need to answer question B. What's the tension in the rope? We focus on the 3 kilogram object to answer this. Why? Because when we look at the free body diagram of the 3 kilogram object, we see that the only unknown force there is what we're required to find out, the tension acting on the 3 kilogram body, which is the same as the tension acting on the 1 kilogram object. In other words, it's equal to the tension in the rope. Now we know that this body is accelerating to the right at 7 meters per second squared. And whenever a body accelerates, we know that there's a net force acting on it, which is causing that acceleration. The magnitude of that net force is equal to the mass of that body multiplied by its acceleration. We know the mass of the body, it's 3 kilogram. We've just calculated the acceleration of the body, it's 7 meters per second squared. So we can calculate what the net force is on this body by just simply multiplying those two together. At the same time, we also know that the net force is the vector sum of the horizontal forces acting on the body. And we know what those horizontal forces are. They are 42 newtons to the right, and the unknown force that we're trying to find out to the left. And Fnet is the vector sum of these two. If we take right to be positive, that's 42 minus the tension. We rearrange this to make tension the subject of our formula. We solve and we find the answer 21 newtons to the left. We know that the tension exerted by one end of a rope is equal in magnitude to the tension exerted by the other, but they act towards the center of the rope. So the tension exerted on the 3 kilogram body is 21 newtons to the left. And so the tension exerted on the 1 kilogram object is also 21 newtons, but now to the right. And so we can give our answer as the tension being 21 newtons. The tension in a rope like this has direction towards the center of the rope. Final question, what's the force exerted by the 1 kilogram block on the 2 kilogram block? According to Newton's third law, the force which the 1 kilogram exerts on the 2 kilogram is the same magnitude as the force which the 2 kilogram exerts on the 1 kilogram. So we could use either the 1 kilogram's free body diagram or the 2 kilograms to solve this question, because they have the same magnitude as one another. But since we specifically asked for the force which the 1 kilogram exerts on the 2 kilogram, let's focus on the 2 kilogram object. Horizontally, there's only one force acting on it, and that is the force that we're asked to find out about. Vertically, it's in equilibrium, so the net force acting on this body is the force on the 2 kilogram by the 1 kilogram. In other words, what we're trying to find out. And this net force will cause acceleration. We know that this body accelerates, the whole system accelerates, and the whole system accelerates together. That's 7 meters per second squared to the right. And it's this force, F on 2 kilogram by 1 kilogram, that is causing this acceleration. And we use that fact to find out, well, what is the magnitude of the force? Because we know that that force is causing an acceleration in accordance to Newton's second law. Fnet equals ma. Fnet is the force we're trying to find out, F on 2 kilogram by 1 kilogram. We know m, it's 2 kilogram, and we know a, 7 meters per second squared. We simply substitute and we find our answer, 14 newtons to the right. So the 1 kilogram is exerting 14 newtons to the right on the 2 kilogram. And so we also know that the 2 kilogram object is exerting 14 newtons, but now to the left, on the 1 kilogram body.